So hello, today we are going to talk about the shortcut and underspecification. This is the sixth talk in the interpretable NLP series. So as a recap, usually we consider the relationship between task performance and the model abilities is that if a model can reach very high accuracy or F1 or very low cross entropy, whatever, it means that they have good ability. No matter what ability that is, have, for example, ability to recognize the positivity of sentiment or recognize the textual entailment, and that the performance, if it can generalize across the trend or depth split or several other very related data sets, then it means that it can generalize well. And both viewpoints are challenged because there are the shortcut learning problem. So to make the NLP models more interpretable, we need to explore more about this machine learning task and their generalizability. So this week we discussed from a model point of view, and next week we will discuss from a dataset point of view. So it was written by Niven and Carl in 2019. They focused on the argument reasoning comprehension task. In each data point, the model is presented with a claim, a reason, and either of a warrant and an alternative. So the reasonings behind these sentences are the reasoning when it's supported by warrant, it leads to the claim. But if the reason is supported by the alternative, then it leads to the negation of the claim. In this example, the claim is Google is not a harmful monopoly. The reasoning is people can choose not to use Google. And if it is supported by the warrant that other search engines don't redirect to Google, then it means that Google can people can choose not to use that, and it's not a harmful monopoly. So it's R supported by W leads to C. But on the other hand, if it's supported by the alternative, which in this case it's a negation of warrant, then the negation of claim is true. So the goal is given C and R, pick a label for the warrant sentence or the alternative sentence. On the experiment, the large models like BERT got very high performances, and the performances were even comparable to human, untrained human. So untrained human reach around 80% of accuracy, but BERT large was able to reach around 77% of max accuracy. Depending on different random seeds, there are different results, and the mean accuracy was a little bit lower, but the max accuracy was very impressive. However, they also discovered that if the BERT takes in only the warrant as the input, they were able to reach 71%. And when they take in both R and W, in this case, they still are not able to perform the complete reasoning chain, because in a reasoning chain you need an R and W and a C sentence, but there's no C here. So without a reasoning chain, they still got a maximum accuracy of 0.75. So it's only 2% of accuracy drop from the full model. So apparently there are some problems here. So the models are relying on something else than the argument reasoning. So what is the thing that they are relying on? The authors propose that it is the statistical cues that the neural models are relying on to make some classification. So they considered unigrams and bigrams as this kind of queues. So for each queue, they occur in different frequencies between the positive and negative data points. So when the models count do some counting, they collect some statistics, and they start to develop this kind of rules so that whenever they see a feature in this queue, for example, the occurrence of a feature, they just give 1 or 0 to the final labels. So this is relying on superficial queues. By relying on these superficial queues, the authors argue that this activity is not relevant to the true task that we are examining. So the true task should be to understand the semantics of the sentences and perform some reasonings of their of their relations and then make some classifications. But when they rely on the statistics of this, they are taking the shortcuts. So how to describe the extent of this statistical queues? They computed some numbers, applicability, productivity, and coverage. So the applicability is that the number of data points where this queue occurs in one label but not the other. And productivity is defined as the proportion of applicable data points predicting the correct answer. So, which basically means that it's the number of data, the proportion of the data points where you can predict a label equal to 1 when you see the queue. And then the coverage is that among all the data points, how many cases are applicable. So how many data points contain this queue. So for the queue not, its productivity is 61% and coverage is 64%. So if you just pick the sentence with not as W, you would be right 61% of the time on the 64% of the data points. So how to adjust for this imbalance in the statistics of these queues? They propose a simple fix, that is to construct an adversarial test set. So if the original sentences are data points are R and W goes to C and R and A goes to not C. So if you construct a C prime equal to not C, then you essentially flip the positive and negative samples. And if you mix the original and the adversarial test set, then the data set becomes really balanced because it's no matter, so if original Q occurs more in the positive samples, it occurs equally, there's an equal surplus in the negative samples, and you mix the two data set portions and you have a very more balanced data set. So essentially by doing this, they remove the effect of statistical cues of that kind. And of course, the models perform terribly on an adversarial test set. So they are essentially taking the chance by predicting like just slightly above 50% on the maximum accuracy. So the good thing is that the if you pass in only the warrant or the reasoning and warrant or the claim and warrant, the results are back to around 50% of accuracy. But the bad thing is that the full model results are down to around 50% as well. So the bridge relies very heavily on these statistical cues. So the authors also proposed a fix to this problem, though. They proposed to add some of these adversarial test samples into the training set, and then it would boost the accuracy of the adversarial test set. So this would be one of the methods that we will discuss in around 10 minutes. So the right for the wrong reason is another evidence. McCoy et al. Considers the natural language inference task. So each data sample contains a premise sentence and a hypothesis sentence. For example, if the premise sentence is the judge was paid by the actor, and the hypothesis is the actor paid the judge, then there were the entailment relations, because the judge was paid by the actor entails the semantics of the actor paid the judge. So if a model predicts the right for the right reason, it should predict entailment because the premise entails the hypothesis. But they showed that many models just predict the right for the wrong reason. They predict, for example, both sentences contain some certain words. So this is the lexical overlap heuristics. So in this paper, they identified 3 heuristics: lexical overlap, subsequence, and constituents. So these heuristics are similar to the statistical cues, but in a more abstract level. So the lexical overlap heuristic is that they assume that the premise entails all hypotheses constructed from the words in the premise. So if you see that the doctor was paid by the actor, and you take the words from the premise and reorder them and construct a hypothesis, the doctor paid the actors, then following this heuristic, you will predict true because the hypothesis is constructed by the same by the words that are taken from the premise. But from the semantic point of view, this is wrong because you flip the subject and the object. And in the original sentence, like the premise is the actor who paid the doctor, but in the hypothesis, it becomes the doctor paid the actor. So there are some scenarios where relying on these heuristics will lead to the incorrect answers. And they collected the Hans dataset, which consists of the scenarios where the models would lead to incorrect answers if they rely on these 3 heuristics. So in each of these 3 heuristics, they consider 10 templates. So in total, there are 30 categories of sentences. More of these examples include, we already saw the lexical overlap heuristics, and in the subsequent heuristics and constituent heuristics as well, they contain both the entailment and non-entailment labeled data. So apparently, the models didn't, they were not very sensitive to this kind of heuristics. So no matter where it should predict the entailment or non-entailment, they just predict one of the labels. So they got almost 100% accuracy on one case, but 0% accuracy on the other case. So in total, the F1 score was about 0. So apparently they classified the heuristic instead of the true entailment relationships. There are more empirical evidence and formulations of this problem. So this is also framed as shortcut learning or the underspecification. So the name of shortcut learning is takes from taking shortcuts, like a lot of humans do in psychology or education, and for example, language exams. And the problem of underspecification describes this problem in more of a machine learning pipeline perspective. So they consider the machine learning pipeline to be underspecified if there are many predictors that a pipeline can return with similar risk. So there are multiple ways to get the same result. You can either be true for the correct reason or be correct for the making the correct prediction from the wrong reason. So both are possible predictors that could be results from the machine learning optimization, and because they got they produce outputs, although with different reasons, the risk or the loss are different, are almost the same. So this pipeline is therefore underspecified. So these two types of framework, when compared together, it looks very interesting to compare these two different perspectives. And up to now, it seems like there are three main methods to address this problem. So you either make the training set harder, or let the models be able to handle the dataset bias, or just train the models on larger data sets. So the Hans paper used the first method as well as the Niven and Kal paper. So there are 30 categories. You add some examples from all these 30 categories into the training set, the MNLI, then you get models with much higher F1 scores. So the models do not just predict true for one for both classes. So they know to predict true for the entailment class and predict 0 for the non-entailment class. So they start to be sensitive to this true feature instead of the superficial feature. So the Hans data is a direct. It's more direct because you already construct the 30 categories, and these 30 categories are exactly those 30 categories that you are evaluating on. However, what if you do not know the types of shortcuts or the nice formulations of the sentences? So what if the sentences are generated by humans instead of from the templates? The counterfactual augmentation is another method. So in this paper, they instructed the Amazon Mechanical Turkers to minimally change the sentences. So to keep the sentences coherent, but to flip their labels. For example, in an example of IMDb, the original sentence was, "The world of Atlantis hidden beneath the Earth's core is fantastic." So this is positive. But when they recast the fact as hoped for, this is one of the methods they summarized to possibly flip the labels. The sentence became, "The world of Atlantis hidden beneath the Earth's core is supposed to be fantastic." So when they add the supposed, it infers or implies that that the world of Atlantis is not fantastic. So they minimally change the sentence, but essentially flip the labels. And the new datasets are harder for models apparently, and this encourages the models to learn the difference that makes a difference. And learn the difference that makes a difference is in the title of that paper. So method 2 was to improve the models to handle dataset bias. So the motivation behind these types of method is that we don't want to train on a harder dataset as the trained dataset. We want to train on the original dataset, but make these models more robust so that it could handle the potentially harder test sets or even unknown test sets. One of the methods is to use ensemble and let the models learn from each other's mistakes. So in one of the models, they set up first they set up a weak model. Let's say it's the W model, because smaller models tend to rely more on the superficial cues instead of digging deep into the semantics and or logical inference or whatever, and then let a main model to distill knowledge from the weak model. So the way they use to distill the knowledge is by using a product of experts. So it's adding their logics before the softmax operation. So and it's an element-wise manipulation. So after taking the softmax operation, the result becomes an element-wise product of logics in both the main model and the weak model. So by doing this, the two models sort of compensates for each other's mistakes. And when you're training the main model, you want to freeze the weak model so that the main model is learned to both optimize for the goal and to avoid the mistakes of the weak model. So the product of experts loss is just a negative log likelihood of the ensemble logics. So the Clark paper just went with the POE loss, and the Sang paper also added a cross entropy loss and optimized for this collective model. So how can the main model correct for the mistakes of the weak model? So this is an intuitive explanation. So there are many classes, and let's say there is a variable j that indexes the classes. For example, 10 class, and j equals to 0 corresponds to the correct target class. And at position 0, if the weak model is small, then the main model should be large enough so that it could compensate. So at other positions, similar arguments could apply as well. So there are also other methods. For example, unlearn the dataset bias by fitting the residual or end-to-end bias mitigation. And I also want to add a pointer here to refer to the dataset debias papers in fair machine learning. So there are some interesting relations between the dataset bias we mentioned here and the bias mentioned in fair learning. So the dataset bias mentioned here is defined as those shortcuts where the models are able to take them and they could reach good performance on this current model, on this current data set. But the models, if they are doing that, they cannot reach as high performance on the other data set because it does not generalize and it does not transfer. So it does not learn the real knowledge, and we cannot assess their true ability. And in terms of fair machine learning, the data set bias is that the models are like getting high performance on this data set, but the high performance on this data set is produced by either for example, the bias in the data collection methods or some currently unfair or imbalanced attitudes in the dataset generation process. For example, the gender imbalance or the race imbalance. And these two types of bias, although they are formulated in slightly different terms, I believe they are the same thing. And although they are not, there are some different mathematical explanations or formulations to the essence of the bias. I believe that there will be a more uniform formulation in the short future, and we can expect to have a more like systematic formulation within 5 years, I think. So the third method is that you pre-train the data set a bit, pre-train the models a bit. The models would be more robust. So this paper found some empirical evidence that if you pre-train the model with a larger amount of text, then when you take this pre-trained model and attach a small classifier and fine-tune that on the challenging data set, they will reach higher performance. So previously, we mentioned Hans as the challenge set for the MNLI data set. And there's also another challenge data set, PAWS, that's collected for the QQP, the core question pair task. And they compare the models of including a bird trained from scratch, eSIM, there's no pre-trained model, and also the model trained with 16 gigabytes of text, a bird base and bird large, and also the Roberta, which are trained with 160 gigabytes of text. So by comparing those models, they are comparing the amount of pre-training. Well, of course, I think there are still some apple to orange comparisons because there are some variance between the training loss of BERT and Roberta in the implementation, but the ideas are solid in general. So comparing the performance on MNLI and Hans, the effect is more obvious that if you pre-train on larger text corpus, the performance on both the in distribution and the challenging set are improved a lot. But this is not that obvious on the QQP dataset. So the performance on the in distribution data are similar, but on the challenging dataset, there's even the improvements are not. There are some improvements from BERT base to Roberta base, but not from the BERT large to Roberta large. And the variance is a bit larger as well. So they are not significantly better. So in this empirical evidence, the pre-training, they show that the pre-training could be helpful, but differs across tasks and models. So what if they pre-train the same model on just on different portions of the corpus? This is what this paper is trying to do. So they considered the specific surface versus linguistic features. So the surface features are really on the surface level. For example, the absolute position is the first token of the sentence. A positive example would be the cat chased a mouse. The first token is the. A negative example would be a cat chased a mouse. So there are this kind of interesting surface level features. And there are also the linguistic features. So the linguistic features are slightly on the on a level that is slightly deeper than the surface features, but they are not touching on the semantic or the level. For example, the morphology. So this S has an irregular past verb. A positive example is the cat slept, and negative example is the cat meal. So by trying to tell, examine whether these models are able to tell apart the surface versus linguistic features, they examine whether the models tend to take the shortcuts. So if a model takes more shortcuts, they are relying on more of the surface features. Otherwise, they rely more on the linguistic features. So they did the sort of inoculation experiment by adding a small amount of disambiguating data into the otherwise ambiguous training set. So an ambiguous training set is one where you can classify by both the surface feature or the linguistic feature. But on a disambiguating data, you will be mistaken if you classify on the surface feature. So you will get 100% accuracy if you only rely on the linguistic feature and disambiguating data. So the disambiguating data tells the model to rely on the linguistic feature instead of the surface feature. So that's why they are calling this disambiguating and the inoculation experiment. And they also evaluated with the linguistic bias score. It's essentially the Matthews correlation between the model prediction and the disambiguating test set. If the score is +1, then the render shows a systematic linguistic bias, and vice versa for the surface bias. The results were surprising. Well, not that surprising though, considering the previous evidence. So the larger corpus helps Roberta to learn more quickly from the disambiguating data. As they increase the number of the size of the pre-training data set, they found that less inoculation or very slightly disambiguating data added to the training set will help the linguistic generalization, which is a larger linguistic bias score towards +1. So a potential interpretation is that when the models have seen more of the text from the pre-training corpus, they know that different patterns exist. And when they see the disambiguating set, in the training data, they tend to discover them and realize that they are the disambiguating data. So they sort of adjust for the inductive bias, and instead of only relying on the superficial knowledge, they are just smarter, and instead relying on the more deeper and more generalizable features. But up to now, these papers are more they are looking for many different point of views, and doing this kind of analysis rely on the a combination of many techniques. And for example, this is a cross-reference from one of the papers in the fault probing talk 2 weeks ago. So they found that when the features is harder to extract by probing methods, they need more disambiguating data or the evidence to learn to generalize this feature. And in their paper, the evidence is that the data points where the positive or negative of the feature does not equal the positive or negative of the label. But so essentially, you can't rely on the superficial features on the disambiguating data. So up to now, there are 3 main methods that I found that are very effective in solving the right for the wrong reasons, or underspecifications, or shortcut problem. But first, the essence of this problem is still under debate. And second, why these methods can solve this problem is still under debate. So I'm very interested in this this large direction of work, and I think in the next few years, I look forward to try to put forward a more rigorous framework. So both the definition of the problem and also the solution of this problem can fit into this framework. Let me stop the recording.